So, I want to begin more or less where I left off last time. Everyone can hear me okay? Yeah?
Yes.
Good.
Yes. Okay.
And you'll recall that we had reformulated last time. We had reformulated the bracket and I'll come back to that in a moment. And we had also given examples of knots K, virtual knots K with bracket K, trivial, or Jones polynomial equal to 1. And I advertised that we would later prove that a lot of these examples, or an infinite class of these examples, would be proved to be non-trivial virtuals, but not classical. And one example of that kind from last time was this culprit here. And this was obtained by virtualizing a classical crossing. And by virtualizing a classical crossing, I mean that I change the direction, or in other words, the sign of the crossing, leaving everything else alone. So the only thing that's changed between these two diagrams is the sign of this crossing. If this, for example, had been a positive crossing, then you see that it is now, because this goes down through, it's now a negative crossing, and we changed the sign. And we showed that the bracket polynomial of a situation of that kind is equal to the bracket polynomial of smoothing away the virtual crossings. But that this had the effect of being the same as taking the original knot and switching the crossing. That's because, and I'll review this for a moment, that's because when you go over here and you have the same bracket, then the diagram is smoothed like this, you see. And upon being smoothed like that, it's equivalent to this. And this diagram, I could put the arrows if I wanted to keep them around. And this diagram, as you see, has been obtained by switch. So what this amounts to is there are two ways to change the sign of a crossing. One would be to simply switch it, and the other is to virtualize. And it turns out that virtualize has the same bracket polynomial as switch. Of course, that means that if you were to look at the bracket polynomial of this knot, it would be the same as the bracket polynomial of the ordinary trefoil after switching. Here's the trefoil, and this went by virtualization, and this goes by switch, which I'll just write as SW. This goes by switch. To this, which of course is equivalent to this, and we'll keep track of regular isotopy. But you see, that's telling us that the bracket polynomial of this virtual is equal to the bracket polynomial of this little curly unknot. And this is the general situation. So we can, by switching, by looking for sequences of crossings that will switch a knot to an unknot, produce infinitely many examples of knots that are have unit Jones polynomial. And I also indicated last time how it turns out that these will be non-trivial by calculating a quandle. But that's the summary. Now, then I was saying I'm going to go on and reformulate this, and then our intent is onward to Khovanov homology. And we will, and even today we will. But I wanted to stop and make a stop in this arena here and show you in just one other invariant so that we can prove without by elementary means that this knot is in fact a non-trivial virtual knot which is not classical. So I want to tell you about the index polynomial for a few minutes and verify a thing or two about that. And that will give you some tool also if you haven't seen it before. So are there any questions about last time other than this quick summary? Okay. So here is what we're going to do, and I'll do an example of a simpler nature, and then I'll do the example that we wanted more particularly. But here's a simpler virtual knot, which we have proved to be non-trivial already in 2 or 3 ways, and I'm going to orient the knot, and then what I'm going to do is I'm going to take a flat picture of the knot, and on the flat picture of the knot, I'm going to define a weight system, and I'm going to do that by labeling the edges of the diagram. And they're going to be labeled in the following, according to the following pattern. If this edge is labeled A and it goes along and meets a right-going edge at a crossing, then the forward line beyond the right-going edge increases the label. If this label meets a left-going edge, then it decreases the label. And you can verify that if you take any diagram at all and start labeling it with integers, this is a Z labeling. If you start labeling a diagram with integers, that it will consistently label. Any virtual diagram, knot diagram, will be consistently labelable. Link diagrams are not necessarily consistently labelable, and that's another subject I won't go into today. But let's just consider this. Let's start here and label that edge 0. So this edge is labeled 0. And then it meets a right-going edge, so it gets labeled 1. Oh, and I forgot to tell you, but you probably guessed, since I try to be simple about virtual crossings, that if you have a label and it goes through a virtual crossing, it just remains the same. Okay. So 0, 1. 1 goes through the virtual crossing and ends up here. 1 is meeting something going to the right and becomes 2. 2. 2 meets something going to the left and so becomes 1. This 1 goes through the virtual crossing, and 1 decrements to 0, and we're done. Now, I'm telling you the rules, and then I'll discuss to some extent what this means in a moment. Then, at a crossing, you may have some weights. Let's suppose you have A and A plus 1 here, and an unknown B and B minus 1 here, right? And then I'm going to define two weights, the W plus and the W minus. The W plus is obtained from, if the arrows go to the right, it's obtained from the right, the arrow on the right minus the arrow on the left. So it's A plus 1 minus B. And the W minus is equal to B minus 1 minus A, the right minus left in both cases. You'll see that these are negatives of one another. Note that, right? That W minus is equal to minus W plus. And now we define a polynomial associated with the knot in the following way. We define for a crossing C belonging to the crossings of the knot. Well, then we have actual crossings, and they have signs, and this is a crossing of sign plus, and this is a crossing of sign minus. And we define pk to be equal to the sum over C belonging to the crossings of k of t to the weight of the crossing, which I haven't defined yet, minus 1, times, then I'll put it over here, I usually put it over on the other side, times the sign of the crossing. And the weight of the crossing is the W sub sign of crossing at that crossing. So in other words, you take the W plus at that crossing, if it is a positive crossing, and you take the W minus if it is a negative crossing. And this polynomial is an invariant of virtuals. Now, having described it that way, that's all very concise. But what I want you to understand is something about what these weights are measuring. So on this example, notice what would have happened if I had taken a little trip starting at this crossing and gone around until I came back to that crossing. And you'll see that there were some virtual crossings present. If there hadn't been, then the weights would have behaved differently. You see, what happened is I went along and I went up because I crossed through that one. And then if this had been a real arrow, then I would have gone back down. And so the increments of the weights would have been balanced by the decrements of the weights, and I would have come out with a weight difference of 0 here. But because of the fact that that it may be that I will have a different number of inputs than outputs on the lines going through because of the virtual crossings, as we saw in parity the last time, these weights can be non-trivial. And because of that, the invariant works. And it's not hard to see that it is invariant, and you may enjoy playing with that. But let us calculate an example. I point out to you that what we got here could be reformulated in more than one way before I go doing an example. One way would be, it is the sum over the crossings of the sign of the crossing times t to the weight of the crossing, yes, minus the sum over all the crossings of their signs, minus the writhe of the diagram. So it is writhe compensated in that way. And you can think of just putting down sign of crossing, t to the weight of crossing, like that, if you're calculating it. Now we're going to need another board in order to do the calculation, so let's do that. I assume you're going to remember everything, and I will get rid of some things. But if, in case you don't remember everything and you want to see it again, just let me know, and I will put it back up. So here we are, and let's make a table of the weights. So for the flat diagram, I make the table. I have the W pluses and the W minuses, and I have the crossings, which I'll call A and B here. And what is W plus at A? Well, it's 1 minus 2, which is minus 1. And what is W minus? It's 1 minus 0, which is 1. Correctly negated from the other. And what is W plus at B? 2 minus 1 is 1. And what is W minus? It's minus 1. So there we are. And now these are both positive crossings. So that tells us that pk is equal to plus t inverse plus t minus 2, because we subtracted the writhe, and the writhe is 2. And this is now this implies that k is non-trivial and non-classical. I'll let you think about other properties such as mirror images and so on later if you like. I just wanted to show you how it can be used to check. Now, what do we know about this invariant? We know that if k, these are facts about the invariant. If k is equivalent to k prime by virtual moves, Reidemeister moves and Dieter moves, then their polynomials are the same. If k is classical, then pk equals 0. The reason for that is that in a classical knot, all the weights are 0. In a classical knot, whenever you check this out, what goes up must come down, and there aren't any virtual crossings intervening, and you'll get 0 weights for everybody. And so once we get non-zero polynomials, we know that we have non-trivial knots. So this is a nice way to prove that some knots are indeed non-trivial and non-classical. There is no way to get rid of the virtual crossing. The genus is definitely greater than 0. So now let's do one more exercise with this invariant just for the sake of completeness and check that example that I showed you. Is non-trivial. So here's our example again. The knot obtained from the trefoil knot by doing a virtualization of one of its crossings. There we are. And we're orienting it. And we're going to take a flat version. And get the weights. So let's start labeling here 0. And then we went up to 1 and came around to here. And then we go up again to 2, and then to here. And then 2 goes up to 3. And 3 goes back down to 2. And 2 goes back down to 1. And 1 comes round and goes back down to 0. We're done. Let's say this crossing is A, this crossing is B, and this crossing over here is C. And we'll make a diagram, and we'll make a tabulation of weights. So at A, we have 1 minus 3 is minus 2, and 2 minus 0 is 2. Those are the weights at A. At B, 3 minus 1 is 2, and 0 minus 2 is minus 2. And at C, here, 2 minus 2 is 0, and 1 minus 1 is 1, 0. No weights at C. This is positive, and that one's positive. So if we call this not K again, then we get pk is equal to t to the minus 2 plus t squared minus 2. Now, the arrive here was plus 1, minus 1, which was a 1. But never mind. Yeah, and the 1, the extra 1, came from the t to the 0 that happened here. So if you're calculating this, you can, in fact, always just normalize it by making sure that the sum of the coefficients of the existent t's is canceled out. The sum of the coefficients should be 0. And you don't have to think right unless you want to. But here's our polynomial. There it is. And it's non-trivial, and that implies that k is non-trivial and non-classical. So here's an exercise for you. Calculate P for another example K prime where the Jones polynomial of K prime is equal to 1. In other words, take another knot, find an uncrossing sequence for it, virtualize on those crossings, and do the calculation and see if P detects it. If P does detect it, then you probably don't have to do exercise part B, but exercise part B is to find a K prime, non-trivial, Vk prime equal to 1, but Pk prime equal to 0. There are examples where it just, the fact that they are non-trivial virtuals is not seen by the invariant P. Okay, so that's an introduction to P and a couple of exercises about it. You will notice that the way I told you how to calculate it, you can calculate it for all the different knots that are obtained by choosing different switchings at the crossings. Because after all, the W plus and the W minus is what you need. So if, for example, you had switched these to negative, why then the polynomial would be minus t to the minus 2 minus t squared minus 2 if you'd switched those two. What if you only switched one of them? If you switch one of these, it should turn out to be trivial, right? Because there would be a Rademacher 2 move right there. What happens if you switch one of these? Well, say you switched A. Then you'd get a t squared, but minus t squared, and plus t squared. So it would cancel out, and you would get 0 for the polynomial. Okay, so this is a good exercise to see what the limitations are of this invariant. Sometimes it's very good at detecting things, and sometimes not, but it's very easy to compute. And it's surprisingly good in a lot of cases. Now back to the normalized bracket, and I'll remind you now, the rewrite of the bracket. So I'll use it right as a square, and it's going to be expanded this way now. A coefficient of 1 on the A smoothing, and a coefficient and a minus q on the B smoothing. The value of the loop is going to be equal to q plus q inverse. And what we found last week is that you can normalize it by defining jk of q to be equal to minus 1 to the n minus q to the n plus minus 2n minus times bracket k of q. And then this is invariant under all Reidemeister moves and detour. So it's an invariant of virtual knots. And in fact, the Jones polynomial in T, its usual variable, usual Jones, is equal to jk at q equal to the square root of t. However, the usual Jones is normal. This is so v circle one component is equal to 1, okay? Because the way we've defined this, the value on a single circle is q plus q inverse. So this is the translation to the Jones polynomial, if you care to worry about it particularly. So I'll call this the Jones polynomial, even though it's not the usual one. So of course we have we now want to write down a state sum for this and show how to build the Khovanov homology in relation to this. You could do, again, for exercise, you should check that this is correctly normalized so that it works with respect to Reidemeister moves. Worth your while. So let me see. I'm going to erase part of this because I'm just going to be staying with the bracket without the normalization for the most part. And we want to write this as a state sum. And I'm going to use first just the ordinary states. So we have the usual bracket states. Then we can say that the bracket of a knot k is going to be equal to the sum over those states, the usual smoothing states, of minus 1 to the number of B smoothings in the state S, where this is an A smoothing, and this is a B smoothing, okay? So I'm still calling them A and B, even though I've changed my letters. The smoothing this way, with regard to a crossing, that's an A smoothing, this is a B smoothing. So we want minus 1 to the number of B smoothings, Q to the number of B smoothings. And then we have Q plus Q inverse to the number of loops. So there's our usual state sum. And then I can't quite recall if I did it last time, but I'll start it from the beginning. We're going to we now reformulate to enhanced states. I'm sorry, that's illegible. Let's spell it so that you could read it. So the key to this is place plus or minus 1 on each loop. So that means that if I had a single loop, it would now become a plus loop or a minus loop. It would split into two states like that. And we will have that the value of the plus loop all by itself is Q, and that the value of the minus loop all by itself is Q inverse. And I think from this you now see the idea, because this represented a loop. And now instead of having a loop to a power in the form of Q plus Q inverse, we're going to have every single loop has a Q or a Q inverse coming from it, just as when you take this to some power, it will be a product of it will be a sum of products of Q's and Q inverses. So let's take a look at one more example, just so we see what will happen here. If I have two loops, then the enhanced states become 4 of them. We could both be plus. We could have plus and minus. We could have minus and plus. Or we could have minus and minus. And this will be evaluated to Q squared, and this one will be evaluated to 1, Q times Q inverse times Q, and Q to the minus 2, so that the value of this is then going to be equal to Q squared plus 2 plus Q to the minus 2, which of course is Q plus Q inverse quantity squared. So the result of that is that if I evaluate enhanced states, then I will be able to obtain the polynomial with one monomial from each state. Let's take a look at it in another example to see how that will work. Let's use the ordinary trefoil. And let's take this state here, which is all A smoothings. But now what would have happened? What happens if these are both plus? And we have these smoothings. Well, these are A smoothings. So then the value of this is going to be 1 to the 3rd power from the smoothings times Q to the 3, because you have Q squared, excuse me, because I have 2 loops, each giving a Q. On the other hand, if I took what amounted to the same state in the old state picture, and I had a plus and a minus, then I would have 1 cubed times Q inverse, and it would be equal to 1. This one was equal to Q squared. And one more in that vein, if I had this and I had minus and minus, then this would evaluate to q to the minus 2. And now if I had re-smoothed one of these crossings, it would give me a minus q. So we need those as well. So maybe we want one more here. We could erase one of these states and do that example. So out here in the other side of some of the states, these are all b's now. And maybe this is plus and that's plus and this is plus, let's say, right? So then from the b's, we have minus 1 to the third power q to the minus 3, because it's q inverse minus q. What did I tell you before? I told you, q, not q inverse, I'm sorry, minus q cubed, because we get a q from the b. And then we have 3 pluses, so that's q cubed. So this is from the smoothings, and this is equal to minus 1 to the number of b's times q to the number of b's times q to the number of plus minus the number of minus, which is what the contribution is going to be from each state, each enhanced state. So every enhanced state is going to give us minus 1 to the number of b's, q to the number of b's, q to the number of plus minus the number of minus. Okay? So we can now write a formula for the polynomial as a whole. That way. So what's my formula? My formula is now that the value of the bracket is equal to the sum over S belonging to the enhanced states minus 1 to the I of S q to the j of S, where I of S is equal to the number of b's in the state S, and j of S is equal to I of S, the number of b's, plus lambda of S, and lambda of S is equal to the number of pluses in the on the loops of S minus the number of minuses in the loops of S. So lambda is the algebraic sum of the signs on the state, pluses and minuses. And that's what we just said here, taking it bit by bit, right? For each of these, you get minus 1 to the number of b's, and then you also get minus 1 to the, you get q to the number of pluses minus the number of minuses. So altogether, you get this j and that I, and you get a sum of monomials. So this is quite nice, and we could do some exercises at another point, maybe next week, of actually writing out a polynomial by cataloging exactly what these are and adding them up. But theoretically, this is certainly an advantage, to think about the polynomial as a sum of monomials. For example, here's something you could think about. right? This is a phenomenon, of course. We sometimes have a large knot, but the polynomial is very small, and it has to do with the fact that one of these terms cancels another term. You could have a term with a certain sign and another term with the opposite sign, but it would have the same j. And you could think about, well, how could that happen? You know, it would be different states, but you could have cancellations like that. And what are the largest terms and what are the smallest terms? So all of those sorts of questions are focused a little better by this monomial formulation than they are by the other state sum. And you can have some fun thinking about that or rethinking it if you've already thought about it in the other terms. So this is our picture of the bracket polynomial from the point of view of the enhanced states. Now let's continue in this theoretical vein of thinking about the enhanced states. Okay, I just wanted to get the picture of the algebra in front of us still. Okay, now there certainly could be a lot of states that have exactly the same evaluations here. So I want to write this in the following way. I want to rewrite this as equal to the sum on S belonging to, I'll just write E for enhanced states, of, and then I'm going to sum on minus 1 to the I, Q to the J, times the dimension of Cij, where, and now I'm not going to sum over enhanced states anymore. I'm just going to sum over I and j. It's a combinatorial reformulation of the above sum. I'm going to sum over I and j, all possible I and j, but there'll only be finitely many, where Cij is equal to, for our purposes, the module generated by enhanced states S with I equal to I of S and J equal to J of S. Now this is just a tautology, right? Just a tautology. In other words, I'm saying for every I and j, it may or may not be the case that I get a term of the form minus 1 to the I, Q to the j. If I do, there might be many of them. So I'm going to collect all the states up that have a given I and a given j, and I'll form a module, all linear combinations of them, let's say over the integers, module over the integers, generated by them, and then I'll take the dimension of that, which just means how many of them were there to begin with. So I could have said, instead of dimension Cij, I could have said number Cij, number ij, the number of states with a given I and a given j. But I make a module out of it. And I make a module out of it for a good reason, and that is I can now rewrite this in the following way. I can rewrite this as the sum over j of q to the j multiplied by the sum over I of minus 1 to the I dimension of Cij. And this looks like an Euler characteristic. Now, I need to remind you, just for the sake of completeness, I'll assume that somebody doesn't remember much of anything about Euler characteristic and chain complex. So at this point, maybe we take a moment and remind you about chain complexes. But this looks like the Euler characteristic of a chain complex. And let me say this, and then I'll backtrack and remind you. We need another slide. But this is just a rewrite of that. So we have that the bracket k can be written in this form. So our bracket got rewritten this way, where this just means the number of states that have a given I and a given j, and I've collected up the i's together and left the j out here. And now, if there were a complex C0j goes to C1j goes to C2j, and so on, like that, with boundary maps. I call them boundary maps even though the indices are going up, but we want them to compose, and I won't put indices on them. But we want a chain complex, and we want boundary composed with boundary to be equal to 0, and the j not changed by boundary. Then the sum on I of minus 1 to the I dimension of Cij would, by its very definition, be the Euler characteristic of the complex labeled by j, because there would be one complex for each j. And then, by the usual homological algebra, this would be the Euler characteristic if we were, say, over the rational numbers to make ourselves life easy. That would be the Euler characteristic of the homology of that, which I'll just write as the Euler characteristic of H dot J. So that means that this thing here, then if that were the case, then this would be equal to the sum on J of Q to the J times the Euler characteristic of H dot J. There would be a homology theory, and the homology Euler characteristic would be the coefficient of Q to the J in our polynomial. So there are a couple of things that I need to remind you about, and other things that I need to construct. The thing I need to remind you about is just a little about chain complexes, so we're complete in the sense of having said what these are, and how they have Euler characteristics, and how Euler characteristic of the chain complex turns out to be alternating sum of dimensions of the homology. So, and then after that, we want to see that this really can be done, and it can. I said if there were a complex, but in fact there is a complex, and that's Khovanov's very amazing discovery that it is possible to create a chain complex, and in the form of that we're talking about, it's a chain complex where the generators of each piece of the chain complex are the enhanced states, and the boundary maps will work in this way. So we are looking at a somewhat complicated structure, and we have to look at different aspects of things and then put them together. And I'm going to take a digression now into a little bit about homology, just a little bit, so we have a remembrance here of that. So usually we have boundary taking some n-dimensional thing to an n-1 dimensional thing. We're raising the index, but this is just bookkeeping. But I'll put it this way, where these are n cells, and these are n-1 cells. And as I said, this is just for completeness that I remind you of a couple of things here. And we want that if we go from Cn to Cn-1, and then we go to Cn-2, and we have a boundary map here and a boundary map here, then the composition of those two boundary maps should be equal to 0. And a good example of this is an abstract simplex (0, 1, 2 through n), where the picture is 0 is a point, and 0, 1 is a little line segment from 0 to 1. This could be any index. 0, 1, 2 is something like that. And of course, higher dimensional things will come up. 0, 1, 2, 3 will be a tetrahedron. And I standardly have my arrows going from, that's a 3 there, this is a 1 here. I standardly have my arrows going from from smaller numbers to larger numbers, and then I have to arrange my boundary formulas accordingly, all right? So, and so on, right? So these are simplices, abstract simplices. And how do we define the boundary of an abstract simplex? Well, let me give you the general definition, and then you'll see everything works out very well. You remove the zero. Oh, I'm going to let I hat mean remove I. All right. So I'm going to take the 0 hat, 1, 2 through n, and that gives me a smaller simplex because the 0 went away, minus 0, 1 hat, 2 through n, plus 0, 1, 2 hat through n, plus and minus and so on, plus or minus, plus or minus, whichever it is, 0, 1, 2, n minus 1, and n hat has been removed. Now, is it plus or minus 1? Well, it's minus 1 to the index, isn't it? So it's going to be equal to, right? If it's even, it's plus. If it's odd, it's minus. So it's going to, and n was the one we removed. So at the end state, it'll be minus 1 to the n. Okay? You should check that the boundary of a simplex is algebraically 0. Let's do one so we see that this actually does happen. This is the granddaddy of all things homological, really. So let's take the boundary of 0, 1, 2. So first of all, that's going to be equal to the boundary of 0, 1, 2. And the boundary is 1, 2 minus 0, 2 plus 0, 1. And you go back to here and you see 1, 2 minus 0, 2, which means you go backwards along that, and plus 0, 1. And so the boundary of it is actually going around it like that in a cycle. And then when you take the boundary again, you see what's going to happen. The boundary of 0, 1 is 1 minus 0, right? The boundary of a simple thing like 0, 1 is equal to 1 minus 0, endpoint minus other endpoint. So the boundaries of these are 2 minus 1 minus 2 plus 0 and plus 1 minus 0. Cancel, 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 and you get 0. So then, if you had a space that was made out of simplices pasted together in various dimensional pieces, but the face of a simplex must be pasted to another face so they would fit together, then you could take a chain complex. You could define Cn to be generated by the n simplices, and you would define the boundaries in this way, and you would have a chain complex. Now for homology. The nth homology of C is by definition the kernel of the boundary from Cn to Cn minus 1 divided by the image of the boundary from Cn plus 1 to Cn. So in other words, kernel of boundary, those are called cycles, just like this was a cycle. And if there are cycles that are not boundaries, then they will survive kernel mod image. But if in the image you find somebody, well, that will be a cycle because it's of the form boundary something. And something that is of the form boundary of something automatically is of boundary 0 and lies in the kernel. So this image lies in that kernel, and the result is that the homology group measures cycles and higher dimensional versions of cycles modulo those that might be actually bounding something in the next dimension up. So that's the picture, the classical picture of homology. And how far away are we from this kind of classical picture of homology in thinking about trying to get a homology group for our knot theory? Well, for that, I'm going to go into another piece of abstraction for a few minutes. But I hope this is clear and what the exercise is. You should do the exercise. The exercise is proving general that boundary of 0, 1, 2 through n is equal to 0. Okay? It might not have been obvious that I didn't prove that. I didn't. I just gave you the formula, and you have to apply twice and see that it all vanishes. Okay? And once you understand that, then you understand that you can define the homology of spaces built out of simplices. And then, of course, there's much in the theory of algebraic topology about how you might take a space that's built out of simplices and show that the homology is in fact an invariant of its homeomorphism type or its homotopy type. And that involves more work. But the basic idea of homology is in the simplex. Our next stop is categories. I'll give you the definition of a category in a moment. No, I better give you a definition of a category right now. Category. A category C consists in a collection O of objects and a collection M of arrows, sometimes called morphisms. To each arrow is associated two objects. Like this. Arrow F source of F, target of F. So let's call this S of F and T of F, if in case we ever need it. So it's just like a graph, right? You have an edge, a directed edge, and there's two nodes associated to the edge in the graph. And then we have some axioms. So up till now, what I've told you is that I have a directed graph, right? And then One, if, I'll use the diagrammatic language, if there's an arrow from A to B, and there's an arrow from B to C, then there exists an arrow from A to C, which will be called GF, as though we were composing functions. So this always exists, a well-defined arrow called GF, as though it were G of f of x. But these are just arrows and not necessarily set maps. Given any A, there exists an arrow 1 sub A. And the composition, well, suppose you had A, and you had a map from A to B. And you also have the map from A to A, the identity map. Let me draw it not quite so circularly so that we can think better. There is an identity map from A to A. There's also an identity map from B to B. And then there's some map from A to B. Then this composition is the same as F. And this composition is also the same as F. We're doing F first, and then 1 sub B. So the identity maps act as identities on either end of the morphisms. That's given. And thirdly, and very importantly, if you have 3 morphisms, getting my pad out of order here a little bit, sorry. G and H that are composable. F can be composed with G, G can be composed with H. Then you have 2 possible compositions. You have H, G, F, right? Writing it in composition order, but it could be H applied to GF, or it could be HG applied to F. And the third axiom is that it's associative. Composition of arrows is associative. And that's a category. And there are many, many examples of categories, of course. You could, for example, think of sets and compositions of maps, or topological spaces and compositions of them, or the paths in a graph, where you compose them by doing one path and then doing the next path. Many, many examples of categories all over mathematics. But I have a particular reason for reminding you about category, because it's related to homology. Let's see. Let's begin by talking about 2 arrows, like that. An arrow from A to B, and an arrow from B to C. And according to category, there would be a composite arrow from A to C. And we might call this arrow F and this arrow G, and then this arrow is GF. And as you see, I have a simplex here. And the faces of my simplex, the boundary of this simplex, ought to be F plus G minus GF. And I'm saying that if I have a composition of arrows, then I get a simplex. Now you see here the arrows and the boundary. But what will happen if we had 3? Does it still make sense? And what should we call the original? Well, I'm going to call the original FG. Okay, so I'm going to say F comma G, and then I'm going to say that the boundary of F comma G is equal to F plus G minus GF. But you're wondering, well, what are the signs and what do I mean here? So let's try one more to see if it works. Here we have F and G and H. And I don't have to name the objects so much anymore. But there's a lot more structure here with F and G and H. There is the composition of F with G, which we called GF. And there's the composition of, there's the composition of H with G, which I would call HG. And there's the composition here. And what about this composition? Well, this composition is HGF. Oh, but it's also equal to GFH. Oh, I see. I've got myself slightly turned around. Where was it? Okay, right there. Remember, we're using function composition order, so this is HG. G first, then I'm sorry. Yes, HG in that sense, right? And this one was GF. Oh, My desire to write them in the usual order is strong, but I wanted to stay with the way we normally write things. So what? Oh, and I probably got them wrong again. So let's draw the arrows and then label them, and then you'll see what I'm getting at. Because after all, it's not the labeling that's important, it's the geometry that I'm showing you that I want you to see. So what I'm saying, there we go. Okay. Now, what I was saying is this. If I had 3 morphisms, 3 arrows, F and G and H, composable with one another like that, then I get some compositions. I get the composition of G and H, I get the composition of F and G, and I get the composition, the triple composition. But remember that we're in a category, and the triple composition is well defined, independent of in what order I do it, right? I could do F and G and then H, or I could do G and H and then F. And that's what I'm indicating here. Now, we want to label them correctly. This is GF. F comes first. And this is HG. And this one is HGF. But HGF is either HGF or it is HGF. And as you see, HGF is what happens on the face of this, on this face, the GFH face. And FHG, HGF is what happens on this face. But this is the same edge. And so instead of being a more complicated geometric entity, it's a simplex. It's a 3-dimensional simplex now. And now let me write down the boundary formula for the composition, which I've written as F and then G and then H, the 3 maps. And here's what we're going to do. We're going to drop the first map to get a GH. We're going to compose in the middle in the 2 possible ways, but change sign. So we're going to, if we compose here, it will be F first, and then G, which means that it has to get written in the other order. I'm sorry about that, but that's just a convention that people follow, right? You do G of F, and then H, and then plus, and then we'll do this composition. That means we leave F alone, and we do GH. And then we will subtract, dropping the last one, FG. And now what I want you to see is that those are indeed what I called the faces. You see, the faces of this are FG. There it is. There's the FG face. And the face always contains some things which I didn't indicate, just like this one, FG and a GF, right? But I called it FG. And then there should be a face GH, and there it is. There's the GH face. And there should be a face GFH, and there it is, GFH. And another face FHG, and there it is in back. So that in general, I'm going to, well, I'll just say it in words. You drop the ends, you compose in the middle, and you drop the other end. So what would it be if there was more? We won't write out the picture, but suppose there was an F and a G and an H and a K, then we would have, in terms of the composition of the maps, we would have drop the F, so we get GHK. Then we get minus sign, and we would be composing, so that would be GF HK. Then we would get plus, and we would get F HG K. And then we would get minus, and we would get F G KH. And then we would get plus F G H. And this, of course, would be four-dimensional. So what I'm saying is that if you have a category, then you also have simplices, and you can think of fitting the simplices together and computing homology, so that categories are directly associated with simplices and homology. Now, you could just take a category and think of the space made by all the simplices of all the different composition lengths that are in it, and look at the homology of that space. Or you could let it interfere with associated algebra. I only mean to show this to you as an idea, which you can think about. But you can think about it in relation to very simple categories. For example, you could think about a category which consisted in one morphism from A to A and all its powers. So then the morphisms would be the identity on A and F and F squared and F cubed and so on. And that would mean that you could think about simplices like F and F and F, and so on. And there's all that geometry already associated with even a very simple category like that. And you can play around with this so that if you see categories, you can think about homology in relation to them. And that is one of the background ideas that I see where we are here. That motivates our construction, but the one we're going to use is not precisely the same as this, but nevertheless, It's analogous to it, and we will later talk about the relationship between this very general idea of simplices and category and the category I'm about to show you that's related to the knots. So bear with me, please. So before I erase this, again, there are exercises. You want to think about what kind of simplices are associated with a category, and what are their boundaries like, and how do they fit together? What is the shape of a category? And you can think of very simple graphical categories like that. And why do I bother you with simple graphical categories? Well, very simple. Let's look at the simplest possible link and ask ourselves what the states look like. Now, I'm not talking about enhanced states at this point. I'm just talking about the usual states. So that means that we can look at the 2A smoothings. And then we can get a B smoothing. And we can get another B smoothing. And then we can get two B's. And this has the form. This is a category. All we have to do to make it a category, here are the arrows, and all we have to do to make it a category is to add identity arrows to each of these, and these states are the objects. So here's a category. And if I wanted to abstract it and look at its structure just as a category, I could say, well, there's an AA element, and then there is a BA element, and there is or object, and there is an AB object, and there is a BB object. And this is the abstract category to which this corresponds in its very special splendor of having the states for this link. But this is called a cube category, and because it's a two-dimensional cube. This is analogous to the fact that we could take a plus b squared, and we get AA, AB, BA, and BB, like that, right? And here's a category, and we're going to be talking about a homology that we could associate to this particular kind of category. And the way we're going to do it is a little different from the general simplicial method that I was showing you before. What we're going to do is we're going to do the following. There will be a module associated to each object. In this case, AA, BA, etc. And then we'll tell you about the boundary maps. But we're going to have a module associated to each one of these, and we already do, because the module is going to be equal to the enhanced states for this. The module is generated by the enhanced states. So that means that an element of the module is like plus and plus. If you put down a plus and a plus, it becomes a generator of the module, just like we did before. And then when we get to 1b, of course, we have more than one of these, and there will be one generator for this, and there'll be one generator for this. So we're going to have a module for this, we'll have a module for that, but we're actually going to add them up, as you'll see. We're running out of time, so I probably should, I want to say a little bit more. Okay. So I've told you how to get a module associated to each one of these, and then we're going to take the direct sum along the vertical of when we have a stack of these, so that we take the mod, so that we have Cij is equal to the direct sum of modules for all states with IBs and a given J, but I could also talk about Ci dot, where I don't worry about the value of J, and then it's just all states with IBs. And so if you're thinking of Ci dot, then we're looking at C0 dot, C1 dot, and C2 dot. And we're going to define a boundary mapping, and then we'll see what it does to the J's from here to here. And we're going to define a boundary mapping from here to here. And we're going to do it by using the arrows in the category. And we're going to do it in a much simpler way, in a sense, than what I described to you before. But I wanted you to see that category and homology are very close to one another in any case in relation to the structure of their morphisms. But what we're going to do here is we're going to have a nice morphism that goes from this module to this one, and another one that goes from this module to this one, and we're going to add them up. And then we're going to add these up, and so on down the line, and we will get boundary mappings that work to give us a chain complex like this. One for each column, where we have a constant number of B's, there will be a module. And different numbers of J's will happen in here. But this is only no B's, this is 1B, and this is 2B's, and that's the form in which our chain complex is going to assemble itself. And we have to stop now because we're out of time, but I will begin next time by working on exactly how we do this to define Khovanov homology. So what is our agenda? We want to finish the definition of the Khovanov homology for classical knots. We want to talk about some examples and ideas and facts, because there are some very interesting facts about the theory. And then we want to look at virtuals and how to extend the definition. And this is a subject where it takes a while to absorb the definition. So that's our agenda for next time, and it will take us most of next time to explain what the problem is in extending this for virtuals and looking at some examples, and then we'll be able to try building on that and see what happens. So I'll stop here.
Thank you. Thank you for the lecture.
Did we have questions? No question. Oops, sorry, I didn't mean to share again.
Oh, there is a question in the chat line.
Just a sec. Is there a family of infinitely many examples such that the index polynomial is non-trivial, but vk equals 1? Yeah. We can give an infinite family of examples. Sure. I'll give you an example next time, but you may be thinking of something that could be harder. What you're asking me is, can you give me an infinite family of examples of knots, all different, each one of which has Jones polynomial 1, coming from using the index polynomial to prove it? Is that your question? Uh-huh. Oh, well, I think I can give you an example right now. But we could ask harder questions. Let me see if I can do that right now. I can unknot this by switching that crossing. I can unknot this by switching that crossing. I'm giving you a sequence of knots with unknotting number 1. Each one has unknotting number 1, and they're all rather similar in their composition. Yeah. So I think that if we were to virtualize this crossing in this sequence of knots, then we would be good. We would have every one of these would be detected by the index polynomial, and probably the index polynomials are all different. But if that example doesn't work, similar examples do. I just don't remember my calculations right now. Does that help? That's an exercise anyway. You could see if that family satisfies your question. What might be more interesting would be to produce an infinite family of examples where the polynomial is vanishing on that family, and nevertheless we're going to find out that they're non-trivial. Okay, I hope there was enough balance between abstraction and concreteness in this lecture. I've given you a lot of concrete things, and in the abstract things, I've given you some concrete things to do, but I realize that it kind of has a funny shape what we did today, and we'll probably find that it begins to take a better shape as we keep talking about it.
Oh, thank you.
Okay. See you next week. Thank you.
Thank you, and see you next week. Goodbye.
Bye now.